Good morning, everyone. My name is Solga Laurent, and I will present my team's work entitled Plexiglass Glove Box for Organic Solar Cells. During this presentation, I will try to fill out some points as the motivation, system design, implementation, final product, experimental results, conclusions, and a few things about me. Before starting the presentation, I would like to say a few words about the meaning of a glove box, which is a sealed room that aims to allow a person to manipulate different objects in an environment with the desired atmosphere. On the sides of a glove box, the gloves are arranged in such a way that the user can put his hands in the gloves and perform a task inside a box without contaminating the interior. The entire box is transparent to allow the user to see what is inside. The application of this product are extremely varied, using it in biochemistry, metallurgy, electronics, geology, pharmaceutical industry, and other well-known sectors. The motivation in our work was to design and implement a cheap and portable glove box for organic solar cells used in lab facilities. Uh, to be cheap and portable. More than that, to be cheap and portable, we want it to be lightweight for easy handling between different rooms of a facility. To offer a quick filling with inert gases, with different inert gases, and to keep overnight a good sealing. So at least 12 hours to have a good sealing for in the glove box. Having a starting point, the price of a glove box made by steel and the necessity of a glove box for the analysis of the organic solar cells, we wanted to design and implement one for the researchers in this field. The first stage in the implementation of the glove box was the choice of a more affordable material from which the glove box can be made. One of the most suitable materials for creating this chamber are safety glass, double glazing, and plexiglass. We chose to use the plexiglass because it offers a very good resistance and it is much lighter than the other options. The dimensions of the design box are 100 over 62 over 65 centimeters and were chosen based on other glove boxes that are already exist on the market. The box is provided with a door on the side and the holes through which the hands will be inserted into the box using a pair of gloves. The second stage was to choose the proper sensors and build the electronic measurement and control system, knowing that we must monitor for important medium parameters inside the box, as the temperature, humidity, gas, and oxygen sensor. So after a large market research, we chose the DHT22 temperature and humidity sensor, MQ2 gas sensor, and ME202D20 oxygen sensor. Among these sensors, a reed magnetic sensor was placed to activate the door, open and close the door. In the last stage, we looked for two suitable solenoid valves because the design box has a small volume of only 0.4 cube meters. It was not necessary to use some big valves. On this schematic, system design among the oxygen sensor, gas sensor, temperature, and the other sensors, we have to look to the main unit which control all these sensors and valves. It's the ATM Mega 328P microcontroller, which has the whole logic implemented inside to control the whole system. The system, based on all these components, we project the system was tested initially on a breadboard prototype and after that transferred into a PCB level implementation, which contains two PCBs that can be seen in this slide. One for the sensors unit, which must be placed inside a box to monitor the inside medium, and one to control and command the unit mounted outside the box. So on the left side, we can see the sensor unit, and on the right side, we can see the command and control unit. All these components and all the PCBs were enclosed in a 3D printed box, as can be seen in this slide. So on the left side, we have the sensor unit implemented in a custom enclosure, and on the right side, we have the command and control unit. The microcontroller receives all the information from the sensors that are inside and redirects it to the display. Also, it controls the relays, which in turn control the valves and the electromagnetic lock. The sensors start the monitorization and the data is read and transferred to the microcontroller and then displayed on an LCD. If the oxygen value is higher than 50,000 ppm, then the valves will open and start the process of argon insertion and oxygen extraction. To speed up the extraction process, a vacuum pump can be mounted when on top of the equipment, as can be seen here. When the condition is accomplished, the valves will close automatically, and inside the chamber will have a hermetic environment ready for the experiment. Using this final product, we started out our testings in a real laboratory environment, taking three experiments. The first two are based on internal measurements of the oxygen level and the gas level inside, and the last one it's taken on organic solar cells. So on the first experiment, the values read by the sensor at the beginning were around 210,000 ppm for the oxygen level, 30 ppm for the gas sensor, room temperature around 35 degrees Celsius degrees, and a humidity around 45%. The entire evolution of oxygen level during the first step is presented in the top graphic. So we started the insertion of argon with a pressure of 1.25 bar for a time period of 7 minutes. And after that, we doubled the insertion for another 2 minutes. We could see that the degrees of the oxygen level is much faster in the case of a 2.5 bar than in one of the 1.25 bar insertion pressure. The 2.5 bar pressure is the maximum pressure allowed in the laboratory where we took the testings. Keeping the valve sealed for 5 minutes, the oxygen level remains constant around 100,000 ppm. After this, we inserted more argon at 2.5 bar, and we reach in 16 minutes the minimum oxygen level of 20,000 ppm that could be read by the oxygen sensor. At this point, we closed the valves for 8 minutes and observed that the oxygen level remained unchanged at 20,000 ppm. At the end of this test, the sensor readings, the other sensor reading were 3.6 ppm for the gas, 36 Celsius degrees for the temperature, and the humidity dropped down to 22.5%. For the second test, the one in the bottom of this slide, we start the whole process from the ambient medium oxygen level once again around 210,000 ppm. After closing the door, we inserted argon at 2.5 bar for almost 30 minutes. When the read oxygen level dropped to 20,000 ppm. At this point, we closed the valves and monitored the oxygen level for 12 hours. Analyzing the data saved for this time period, we found that the oxygen level was kept at almost 20,000 ppm for 5 hours, and after that we had small changes every hour. After 12 hours, the oxygen level was around 20,000 ppm. So it means that it's very close to the starting point of 20,000 ppm. And after these experiments, we take a real experiment for organic solar cells. So this last test was taken with 8 organic solar cells, and after measuring the initial uh, conditions, 4 of them were introduced in the glove box and kept at 20,000 ppm oxygen level medium, and 4 of them outside the box for 12 hours. After this storage time, the organic solar cell were measured again, and the results revealed a decrease of the efficiency with 20%. We can see that the 4 cells are keeping an efficiency with a drop of efficiency with a maximum of 20%, and the other ones, the last 4 in this table, shows a drop with almost 70% because of the high reach oxygen level. In conclusion, we can say that we implemented successfully a glove box using materials, a lightweight material as the plexiglass of 6 mm thickness. The oxygen level remains constant at a low level of almost 20,000 ppm for for 12 hours, for at least 12 hours. This is the 20,000 ppm. It's the minimum oxygen level that can be measured with the sensor that we chose for this application to be cheap and to be suitable for the organic solar cell production. And we tested out the environment, the glove box in an environment with solar cells, which proves that being a medium with rich in argon, we can keep the organic solar cells for a high period of time compared with those that are left outside of in an fully oxygen medium. As a price, from the pricing point of view, we have a production value of around 1,000 euro, which is much less that we can find on the market, where a glove box it's around maybe starting from 10,000 euro and going up to 50, 60,000 euro, depending on how big they are and how many sensors do they have inside of them. Before ending my presentation, I would like to thank you and to telling you that I'm a lecturer in the Technical University of Cluj-Napoca from Romania. My main field of research is optoelectronic applications, organic solar cells, and fiber optic sensors. Those who would like to have some research in this field are very welcome to write me and to find a common subject in these fields. Once again, thank you very much, and I wait for your questions.